So last time we saw the concept of a function, or introduced the concept of a function, and it was quite an elaborate thing. And I've left here the kind of the proper formal definition of it. Let me kind of talk through it again. So a function f is kind of two pieces of data. First of all, it's a domain, a choice of domain, and a domain is just a subset of the real numbers. So it could be anything at all. But really what a function is if you take some number in the domain, let's say x, the function is some rule which associates to it exactly one number that I'm going to call f of x. And this is just notation, this is f of x. It's notation for the number associated to x in the domain. So maybe I'll just hammer home the point here. This x here in this side is in the domain. So if I take some x in the domain, f of x is some number associated to it. And we saw last time functions can come from very different places. If I give you some formula, if you want, involving x, then that can give you a function, because you could think about the output of the function f of x as just the value of the formula for that given x. Or you could have f of x as something completely different. You could have x as, let's say, time, and f of x as the temperature at that specific moment in time in some location. So this idea of some rule which associates an output to an input is what a function is, and it's ridiculously important, right? The reason it's so important really is because it's going to turn up throughout all of the sciences. The way mathematics interacts with the sciences is through functions largely. So we want to kind of understand functions in as much depth as possible. Calculus is the study of functions in a lot of depth, really. And to really get going in calculus, you need to understand the basics, the basic definitions, the basic properties of functions, and you need a kind of a collection of core functions you're really familiar with, which is what we're going to look at throughout the rest of the course. So first of all, an important point is this. The output f of x is exactly one number. There's a unique output to a given input. So this is very important. This is part of the definition of the function, if you want. So what that means visually, and I think you should always at least have a visual interpretation of things like this. So important. Classic thing to kind of overlook. Each input has a unique output. It's a unique output. Exactly one. So in particular, if you've got this picture we've got going, and I have x here, it is not possible to have two potential outputs. So you could not have this going on. Right? That does not make sense. That is not what a function is. A function can only have one output for every input. Just like a machine, really, right? I mean, if you feed something in, you get one thing out. Depending on the machine, I suppose. But anyway, that's the rules. This is part of the definition of a function. You can't have two outputs. So let's do an example you're actually super familiar with. Maybe a non-example. So for x greater than or equal to 0, let's define f of x to be equal to the square root of x. Now, does that make sense? First of all, I'm assuming x is greater than or equal to 0, so great, there are square roots. But this is no good, because we know for positive numbers there are two square roots. The square root of 1, well, 1 squared is 1, but so is minus 1 squared. So this would have to be either plus or minus 1. So this is no good. This is not a unique value. This is two values as an output. So this is not a unique value. So f is not a function. Now, there is a fix to this, obviously, one that we're already familiar with. The fix is, well, let's just take the positive of my square roots. It's what we do when we define my radical notation. So the only problem is the two potential things, the plus or minus. So just define f of x to be the positive square root. Okay, nothing wrong with that. So by convention, remember this is always the positive. By convention, always positive. All right. Now this leads into something interesting. If I give you a formula involving x, that basically looks like a function because it's some sort of recipe or rule which, given an x, gives me another number. But remember, part of the information of a function was the domain, right? A function has a domain. So if I just give you a formula, I'm not really explicitly giving you the allowable inputs, am I? So we have to make a convention here. So if I give you a formula, we're going to decree, unless otherwise stated, that the domain is all possible x that make the formula make sense. So here's a convention. If the function, let's say f, is given by a formula, some kind of algebraic formula maybe. So for example, e.g. f of x is equal to the square root of x plus 1, just as an example. So if I say my function is the square root of x plus 1, I'm giving you the rule, but I'm not really telling you the domain, am I? And that is part of the information you have to be given. So the convention is the domain is just as many x's as will make sense. So the domain is all, the domain, I maybe should say, unless otherwise stated. So sometimes you might say this formula with this restricted domain. That may happen, but I should say the domain unless otherwise stated is all x such that the formula f of x is defined. So we kind of assume it's the maximum possible, if you want. So just as an example, this example, well, the square root only makes sense if you're taking square roots of non-negative numbers. So the domain would have to correspond to x plus 1 is greater than or equal to 0. So this is if and only if, of course, by adding minus 1 to both sides, preserves the inequality. This is greater than or equal to minus 1. Okay, so what does this tell you? This tells you in this specific instance, the domain is the interval. It's infinitely long, but it's closed on one side. What is it? From minus 1 to infinity. Okay, but we will see examples where we have a formula and I say, okay, let's not take the full possible domain, let's restrict it to something. We'll see this kind of turning up a bit later on. Really, practically speaking, the common issues that really turn up, so the common issues, when dealing with formulas, at least in this class, I mean, basically things like square roots or even nth roots of negatives, that's not allowed. So square roots of negatives, that's going to mess things up. Zero denominators, same kind of story. It's not allowed. And another one, a little bit more fancy, you can't take logarithms, for example, of non-positive numbers. So logarithms of non-positive. That's inclusive of 0. Those really are the main cases that turn up and the types of formulas that you'll be seeing. So something I do want to say about this is if I give you some formula and I say what's the domain, that can be a really difficult thing to work out. In fact, from experience, at the beginning of your calculus classes at university, there'll be problems where you're asked to find domains of quite elaborate expressions, and it's a difficult thing to do, right? It really requires detailed understanding of functions and the different operations on them. That's something I'm going to look at in a completely separate video, right? Because it is difficult. But it's important to be aware that the convention is, given a formula, unless otherwise stated, the domain is kind of the biggest one possible. It's all x's where the formula makes sense. So let's do a really simple example. Really simple, just to illustrate a few things. So examples. So let's do what's the domain. In fact, no, let me do both the domain and the range. Remember, the range is the possible outputs of a function. So what are the domain and range of the function f of x is equal to x squared plus 1? Now, this is something I kind of want to mention as well about notation. The function really is f, right? And f brackets x is the output of the function. So I'm going to be pretty loose about this. It's a pain to write the function f on its own. It's much more sensible often just to write the function f of x. So I'm going to be a bit loose in my notation between the function and the output of the function. So very often I'll say, we'll think about the function f of x. It's just a tiny notational point. It really doesn't matter, but it's something to be aware of. Technically, the function is f. If I'm writing f of x, it technically means the output, but I'll be kind of interchanging between the two. So you've probably seen this before. A function is f of x. Technically, it's the output. It's just we're a bit lax in the notation. Okay, so let's do the domain of this guy. Well, I've not stated anything otherwise, so the domain is all possible x where it makes sense. I mean, there are no issues whatsoever. I can square any number and add 1 to any number. So x squared plus 1 makes sense for any number x. So this implies the domain is equal to everything. So I'll use interval notation to be succinct. So the domain was super easy here. We had no issues at all. What about the range? Now, things get a lot more hairy when we're dealing with ranges. What we're going to see is actually finding domains of functions is something which is relatively elementary. It could be very difficult, but you can do it using pre-calculus techniques. However, finding ranges of general functions, finding the all possible outputs is something which we'll have to wait really until significantly later on in calculus. But under certain circumstances we can do it. So let's just make some observations. So if x varies, so we've kind of got to think quantitatively here. We've got to think about the nature of the expression x squared plus 1. What possible values can it take? So we're trying to work out what numbers that could be. So if x varies through, well, all possible inputs, that's this. What about x squared? Well, x squared can't be anything, right? A square is always positive. So this means the following. X squared can vary through any non-negative value. X squared can takes all values in the interval 0 to infinity. And that's inclusive of 0, of course, because 0 squared is 0. So square brackets there. So if I was just asking this question for x squared on its own, the range would be this. It would be the interval closed bracket 0 onwards in the positive direction. But if I'm adding 1, what does that mean? Well, this would imply that the range of x squared plus 1, that function, equals what? It has to be this, but bumped up by 1, doesn't it? So I'm adding 1, so everything gets moved up. So I needed to think carefully about the nature of the expression x squared plus 1. I needed to look at it and say, well, what possible values can it take? What do I know about numbers? I know when I square them, I'm positive. I know when I square any number, I can always get any positive number. Right? You can always take square roots if you want of all non-negative numbers. So it was difficult, this example. And if I did something like, I don't know, so if I went back to that example I did in the last video, if I started with this instead, then I'd be in a world of horror because it's so much more difficult to think through this problem now, because sure, the top can take any value, at least greater than or equal to 1, but the bottom is going to vary all over the place. And the ratio, it's incredibly difficult to work out what happens. So, as I said, really finding ranges in general is much more difficult than finding domains. And this is something that's going to have to wait until really more sophisticated material is covered in calculus. So this is generally much harder to determine. Much harder to determine. It can be much more difficult. Okay, so let me kind of talk through a few subtleties here about functions, things that I think people can have misconceptions about. Certainly I've seen, and I want to kind of clarify them now. So as I said, a function is two pieces of data. It's a choice of domain, D, and for every point in the domain, a rule which associates, or should I say a rule which associates to every point in the domain some number, some output. Well, the domain is just any subset of numbers. It could be anything at all. So it's perfectly possible it could be discrete. So it may not be an interval or anything like that. It could be a kind of a series of discrete points. So some functions, some very important functions, have discrete domains. Or indeed ranges. And when I say discrete, well, what I mean by that is the opposite of intervals. So really your points in your domain are kind of isolated single points. That's what discrete means essentially in this context. So as an example, whole numbers. On the number line, they are kind of separated from each other. Each is their own little planet. They don't continuously move into each other. Or integers, same thing, same concept, just a different word. So just as an example, so I'm only telling you this to really make sure you understand domains can be any subset at all. It doesn't need to be on an interval. So let's do the temperature. Again, I'll do it in Fahrenheit, despite the fact it should obviously be in Celsius. Let's say on the hour. On the hour between noon and 6 p.m. So imagine that's the information I want the function to gather. So if I was checking the time at every single moment between noon and 6 p.m., the domain would be, well, if I fix the units of time to be 0 at noon and in hours, the domain would be the closed interval from 0 to 6. But I'm not doing that. This information is only going to be captured on the hour. So in this case, the domain is what? Well, it's going to be 0. I'm going to do it in hourly units starting at 0 at noon. 0, 2, 1, 0, 1, 2, 3, 4, 5, 6. It's that collection of numbers. So, of course, this represents noon. And this represents 6 p.m. Now, of course, there will be times between these, but I'm not capturing that. I'm only capturing what's happened on the hour, which is really how these things work in reality, isn't it? Right? Because if I have some sort of temperature monitor, it's going to be checking at fixed intervals. They could be very quick. It could be once every second, or once every 2 seconds, or once every millisecond, but it's still going to be discrete. So experimentally, generally speaking, the functions I'm going to get will have discrete domains. And same thing here. The range is discrete as well, because it's finite. The range is just whatever these numbers are. So f, whatever the temperature is then, I don't know what it is. Could be anything. I'll write them all out. So the range doesn't need to be some nice continuous interval or anything like that. Very, very important you understand that. Next, and this is actually super important, and it's the kind of thing which, when you learn about functions first, is totally ignored, and it's something I really want to laser in on because it causes huge confusion. Now, we've talked a lot about equations up until now. And equations are expressions to represent equality between two concepts or two values. And they've always meant the same thing. It's always been two numbers, right? Some number on the left, some number on the right are equal to each other. And of course, the number could be expressed in some sort of complicated way using some weird formula, but equality has always meant equality of numbers. So now I have a concept which is quite a bit more sophisticated than just a number, a function, right? It's this new gadget I've kind of started to think about. And we need to decide to ourselves, what does it mean for two functions to be equal? Truly equal. So two functions being equal means that they just have to be the same in every possible sense. They've got to be exactly the same. So that really means two things. It means they have to have exactly the same domain, and they have to be exactly the same rule when I'm looking at inputs in that domain. So it doesn't seem too important, but it really is important. Two functions, we'll call them f and g, are equal as functions. So I would write this down. I would write f is equal to g if the following is true. If both, so one, they have to have exactly the same domain, right? The domain of f is equal to the domain of g, and so two things, and this one is more important really, but you certainly need the first. They've got to be exactly the same rule. So that means f of x must be equal to gx, not just for some x, but for every x. For all x in the domain, the shared domain. This is incredibly important, because the concept of equality of things in mathematics is just everywhere, and you need to understand what it means for two things to be equal to each other. And for functions, it's more complicated than just numbers. So you could have two functions which are equal for some specific value of x. Some specific value of x where they're the same. Okay, so before I do any examples, let me just make sure this is kind of highlighted. This is very important. So let me just give you just kind of some non-examples. So some non-examples. Let's take the function f of x is equal to x squared. And then let's take the function g of x is equal to x plus, let me think of something which is going to work, x plus 20. Okay. Now you look at these two guys, oh, they're not the same function because they just are a different looking formula, but you can be kind of messed up by that. Maybe you could rearrange one into the other format. And that's not actually the same case. Well, that's not actually the case here, but let's just make sure we understand what we're already saying here. First of all, the domains are the same. Okay, so first of all, the domain of f, I'll just write it like this, the domain of x squared, so this is me being a bit loose with the notation, is equal to the domain of x plus 20. They're both the same, it's everything, right? There's no problems at all. Are they the same rule? Well, let's just take a moment. Well, let's just check to see if they're equal anywhere. So let's imagine I feed in 5. So I feed in 5 squared is 25. I'll feed in 5 into this. This is equal to 5. I'm just choosing 5 at random. This is 25. Oh, brilliant, they're the same. So they're the same function. Completely wrong. These two functions are the same only at the point, well, maybe not only, but they're the same at the point 5. That's what I've got here. It needs to be the same absolutely everywhere. Right, it's no good if it works at 5. Let's do another example. Let's just feed in 1 and see what happens. So if I do f of 1, that's equal to 1 squared. If I do g of 1, that's equal to 1 plus 20. So this is, of course, equal to 1. This is equal to 21. They're not equal to each other. So this tells me 2 is not satisfied. This tells me it is not true. 2 does not hold. They aren't equal to each other. At some point, no good. They've got to be the same absolutely everywhere. So I know that kind of feels really obvious from the fact that these formulas are so different, but technically speaking, if we're going to think about this really precisely, in order to be completely confident they're not the same, we should check some value doesn't match up. So there is a difference between two functions being equal and two functions being equal for some specific input. We'll talk about this next time. See here, these functions are the same. The output is the same if the input is 5. But that's not enough to be equal as functions. They need to be much more complicated, right? So all of this tells you f and g are not equal functions. They're equal, the output is equal if the input is 5 for both, but that's much, much less information. Let's do another example. So you see, I'm doing this because it's a bit subtle, and it's the kind of thing that just is swept under the rug when you learn about this in high school. So here's a really good example, one that has caused many problems in midterms in first year calculus classes. Let's imagine I have the function f of x, super simple, equals x. Now let's imagine I have the function g of x, so I'm going to do something mad. I'm going to write this as x squared divided by x. Okay? So you look at this and you say to yourself, okay, I'm an expert in laws of exponents. What do I know? Well, x squared divided by x is x by the usual laws of exponents, so yeah, they're exactly the same. That is not true. So let's take a moment to look at this very carefully. So what do we know? When I'm doing laws of exponents, I need to have things like, well, bases can't be equal to 0 necessarily, right? You can't be dividing through by 0. So if I want to invoke the law of exponents, I can't have x is equal to 0. So if x is not equal to 0, then it is true that x squared over x is equal to x. That's just a law of exponents, the quotient business, where you take 1 away from 2. So this would just be b to the a divided by b to the c is equal to b to the a minus c. Of course, assuming b is not equal to 0. All right, so what's the issue? So the issue basically is, if I want to write this down as x, which I kind of desperately want to, it's only going to work if x is non-zero. So technically, this function, even though the algebra is telling me, oh, it's just going to be x, it's not x. The function gx is kind of a bit subtle. We're going to have to define it pointwise, I think. Or piecewise, sorry. It is x, of course, if x is not equal to 0, just by the law of exponents. But if x is equal to 0, I'd be dividing through by 0. It would be 0 over 0, undefined. Undefined if x is equal to 0. Okay, why? Well, of course, it's 0 divided by 0. Doesn't make sense. So even though the algebra says they look the same, they're not as functions. So the domain of f is equal to what? In fact, I'll just write the domain of x. Slight abuse of notation. I mean, anything, right? There's no issues here. It's the whole thing. However, the domain of x squared over x is equal to, well, it's anything apart from 0. So let's write it like this. It's a little bit cumbersome, as we've seen, but this. And these are not equal to each other. That means these two things are not the same function. They're incredibly close to each other, but essentially the second one has had a point removed from the domain. So this tells you that f and g are not equal functions. They're close to it, but they've got different domains. Incredibly small difference. Super subtle, right? But it's vital you understand this, right? When you talk about two functions being equal, it means their domains are identical and the outputs are exactly the same for every single input. It is not the same as saying f of x equals f of g, f of x is equal to g of x for some x. It's got to be true for every x in the domain, and the domains have to be the same. So they've really got to be just totally and utterly identical in every way. So there's quite a few subtle things about functions. Next time we're going to look at more detailed properties of functions.